Today we're going to give some hints about how regular expressions are used in practice. I'm going to mention some of the extensions that are found in various Unix commands. I'll also talk about some specifics of text processing algorithms and concentrate on the important task of lexical analysis, that part of a compiler that looks at the entire program being compiled and breaking it up into tokens, which are sequences of characters that logically belong together. Many systems use regular expressions of some sort to describe patterns. Often these are embedded in the proprietary code of a company, but there are also some quite visible ones, such as a number of Unix commands. I'm going to tell you one particular story involving proprietary software before moving on to generalities regarding text processing. Junglee was a startup founded by 3 of my PhD students and 2 others in 1994. At the time, the web was really new, and they had the idea of building systems to integrate web pages into more useful products. They were doing that for about 2 years when they got a contract from Yahoo to build a facility that would let Yahoo visitors search for books and get a table giving the price, delivery charge, and delivery delay at different booksellers. Immediately upon deployment of that product, Amazon bought Junglee in order to shut down the comparison shopping capability. Interestingly, Amazon did not understand that I bought from them not because they were the cheapest, but because I was confident that they would deliver what I asked for and deliver it on time. And apparently I was not alone in that thinking, but the world of online commerce was new, and Amazon could not be sure of the impact of automated comparison shopping. An interesting sidelight, Amazon actually got good value for Junglee because one of its founders, Anand Rajaraman, while at Amazon, was the inventor of Mechanical Turk. But the first paid work that Junglee got was a contract from the Washington Post to produce an online table of the employment opportunities offered by companies that were placing print classified ads at the Post. This job was not trivial. Junglee had to go to several hundred websites and extract the information about each job automatically. If you look at one site, you can probably figure out how to do it, which links to follow from the home page to get to the employment pages, and once there, how to navigate in the HTML source text to find the critical information about the job, such as the title and salary. But you need to do this for each site, and to make matters worse, the Junglee guys discovered that these sites were evolving. That is, not only the jobs changed, but the structure of the pages or even the whole website changed. The result was that approximately once a week, the reader for any given site would break and have to be redesigned. So the Junglee guys developed a regular expression language for describing how to navigate a website to extract the information they needed. The input symbols were the usual characters such as letters, so they could look for important words like salary. They also treated HTML tags like OL, that is this, as input symbols because they gave important hints about the page structure. For instance, a page might say, send salary requirements to, but that doesn't indicate the salary for a particular job. But when you get to a list of jobs, and that is indicated by the ordered list tag, that's the OL, and only after that does salary mean that the number following is a salary for a job. Another important kind of input element is a link, which indicates that it's necessary to move to another page. Once this regular expression language was implemented, it was easier to write regular expressions to find key information like title and salary than to write the code to process web pages directly. Thus, there was an increase in productivity as they added sites to their database. Moreover, when the site changed, it was relatively easy to modify the regular expressions to track the changes in the site. The architecture of the system developed at Junglee appears in many places. The input language is regular expressions plus actions, which are arbitrary code that is executed when the regular expression is recognized. In this case, the actions would be things like return this integer as a salary. The regular expression is compiled into a DFA or sometimes into an NFA that is simulated, effectively by executing the lazy version of the subset construction as needed. Simulation of the DFA or NFA goes on exactly as we have described it theoretically. Each input symbol causes a state change and nothing more. The magic happens when an accepting state is reached. Then the associated action is executed, and this action allows the regular expression processor to interact with the rest of the world in some useful way. We're now going to talk about the Unix extensions to regular expressions. There are many commands in Unix that have some sort of regular expression notation for input. An important example is the grep command, which stands for Global Regular Expression and Print. Most of the regular expression-based languages, even though they have extensions to the notation we've covered so far, define only regular language. There are also some commands that have additional extensions that allow non-regular languages to be recognized, but we're not going to go into these features. Incidentally, it is no coincidence that regular expressions figure heavily into the original Unix commands. Before he did Unix, Ken Thompson had worked on a system for processing regular expressions by converting them only as far as an NFA and simulating the NFA in code. We're now going to meet some of the Unix extensions to regular expressions. You can put brackets around any list of characters as a shorthand for the same characters connected by plus signs in the notation we have used until now. You can also describe a sequence of symbols that are consecutive in the ASCII order of characters by giving the first character a dash and then the last character. For example, A-Z, that's this, stands for any lowercase letter because the lowercase letters have consecutive codes in ASCII. You can represent any letter by putting dashes between lowercase a and z, and the same for uppercase. That's this. Okay, notice that the upper and lowercase letters are not consecutive in ASCII, so you cannot represent these 52 characters with a single range. Incidentally, as we see, characters like brackets and dash have special meanings in Unix regular expressions. So if you want to use one of these characters as itself, you need to precede it by a backslash. So for example, slash left bracket is a real left bracket. It's not the left bracket that you find in range expressions. And the character dot or period is shorthand for any character. Here are some more Unix changes to the regular expression notation we learned. Okay. The union operator is actually represented by a vertical bar instead of the plus. But the plus symbol is another operator used like star and meaning one or more. That is, in the Unix notation, E plus, that's that, is shorthand for E concatenated with E star. So for example, A-Z all plussed means one or more lowercase letters. The question mark operator is also used like star but means 0 or 1 of. That is, E question mark is shorthand for E plus epsilon. So, for example, AB in brackets question mark means an optional A or B. We would write it in our original notation as A plus B plus epsilon. You may remember our DFA example for recognizing strings that end in ing. It involved a lot of explanation as we considered where to go from each of the states that represented some progress toward finding ing. However, there is an easy regular expression for the same language using the Unix dot. It's just dot star ing, like that. Okay. Or even if we didn't have the dot in our notation, we could simply replace it by all the legal input symbols connected by pluses. In fact, it's even much easier to design an NFA for this language than it is to design a DFA. Okay, here is an NFA. Essentially, it guesses when it has seen the I that begins the final ing. Thus, even on an input like the first I in skiing, it can remain in the start state. That is, it can go from the start state to itself on an I if it likes. And in fact, it always does like, because the NFA always does everything. Okay, it can remain in the start state on the first I and then only travel to the right, that is here, on the second I. There's no need to worry about what to do in a state like one that represents the I is the discovery of I and N. Where do you go if the next input is not G? It doesn't matter, because you'll still be here, and another sequence of states will get you where you actually need to go. Now let's talk a little bit about lexical analysis, the breaking of an input program into its basic units called tokens. For example, every identifier in a program is a token. Likewise, the reserved words like if or while are tokens. Many single characters are tokens by themselves. In typical programming languages, semicolon is a token used for separating statements, plus is a token indicating addition, less than is a token by itself indicating the less than comparison operator. There are also multi-character operators such as the less than or equal sign, which together indicate the less than or equal comparison. There are tools like Lex, or its open source version Flex, that let you write a regular expression for each token. You can also provide a piece of code as an action to be executed when an instance of that regular expression is recognized. For example, the code for when an integer is found might simply return that integer. As an example, the expression for identifiers might be the one shown here. That's this. Using the Unix notation, this expression describes identifiers as any letter, that's this, followed by 0 or more, the star, letters or digits. In many languages, identifiers allow some more options. For example, underscore might be included as if it were another digit, so it would just appear in this list here as an underscore. In Lex, you write an action, which is an arbitrary code to be executed when the regular expression for a token is matched. In the simplest cases, all this code does is return an integer code representing the token found, but the action might be much more complicated. For example, if an identifier is found, the action might involve installing that identifier in a symbol table where all identifiers used by the program are stored. When building a lexical analyzer using regular expressions for the tokens, there is some resolution of ambiguities that need to be faced. Two examples are illustrated here. For one, reserved words like if also match the expression for identifiers, but if is not a legal identifier, so we have to make sure the lexical analyzer does the right thing on if. Okay. For another, when we see less than, we don't immediately know if it's a token by itself or part of a larger token, which would be less than or equal in this case. We need to make sure we don't prematurely declare victory and return the less than when less than or equal is intended by the programmer. Okay. A good architecture for building a lexical analysis code from regular expressions is to start by converting each regular expression to an epsilon NFA. Each of these epsilon NFAs has its own final state with which the action for that regular expression is associated. We combine all these epsilon NFAs by introducing a new start state. The start state has epsilon transitions to the start states for each of the NFAs. Okay. It looks something like this. Here's the new start state. Here are all the old start states and their automata, and we just put transitions on epsilon to each one of them. Okay. All the final states of the NFAs remain final, and they each have their associated actions. So, for example, these are all final states. An NFA can have several final states, in fact. After that combination, we convert to a DFA, or perhaps an NFA without epsilon transitions, which we will then simulate. Okay. We need to give the regular expressions an ordering, and this ordering determines the priority among actions. A typical ordering puts all the reserved words ahead of identifier, so that way, if the DFA discovers that the next token is if, it in principle does not know whether to execute the action for the reserved word if, or for identifiers, or both. But the fact that if takes priority over identifiers says that this token should be treated as a reserved word and not as an identifier. However, to make all this work right, the DFA actions need a special ability. The ability to take an input symbol it has read and put it back at the front of the input stream. That input will then be read again, typically the next time the lexical analyzer is told to look for the next token. Here's an example of why the ability to restore an input symbol just read back to the front of the input is important. Suppose the lexical analyzer is told to find the next token, and the first character it reads on the input is the less than symbol. It has to read the next input, and if that input is an equal sign, then we can be sure the token is less than or equal. Okay. But if the input is anything else, for example a blank, a letter, or a digit, then that character must be put back on the input and less than by itself declared to be the token. For another example, if the lexical analyzer has read the characters I and F in its quest for a token, it might have seen the reserved word if. But we won't know until it reads the next character. If that character is a letter or a digit, anything that can extend that identifier, then we do not have the reserved word if, we have a longer identifier. However, if the next character is not one that can extend that identifier, such as a blank or a left parentheses, then we really do have the reserved word if. In that case, the next character must be pushed back onto the front of the input.